start recording and put everything away. So James, I did not fix your problem, I know. Let's see what we can do about it, okay? So I'm gonna get ready with my presentation. Let it be short. By the way, a quick feedback about lab 1. I can see that lab 1 was okay for most of you. I was not very happy with the results I shared with you. So the results I shared with you were basically not clear. So in the coming labs, it's gonna be more clear. All right, James, that's good. It's gonna be more clear for many reasons. One, it's gonna be more data related, like numbers, I mean quantitative, which means you will have less difficulty getting it through. And maybe I'm gonna do the measurements myself to make sure everything is okay. It could be for some labs, I'm gonna do the measurements on the video and you will take the measurements while watching the video. But I cannot do that for all the experiments, especially the long ones. For this capacitance and dielectrics, I will simply share the values with you, okay? And this lab has a lot of data analysis. So as you can see at the end, there's an appendix where I want to give us some classwork to try. Okay, let me fetch your name before I start because I want to talk to you while, okay. My screen is so small and I want to put everything on it. I just want your names before I start because it's awesome to have your names next to me. Okay. You guys are ready? So we have lab number 2. For some reason, I feel we need to go slow. So if we need to go slower than this at some moment, I will let you know. What is lab 2? You will have to deal with a lab report. So this is a picture of a lab report that I'm gonna share with you. But anyway, you already have the whole packet of manual and lab report. So which means I may not share every lab alone since you have the whole thing. You take what you need and use it as a template. This lab is practically long. You have part 1 and 2 and 3 and 4. That's why I wanted it to be explicit and visible. Part 1, you will deal with the capacitance versus the plate separation. You will vary the plate separation and you will measure the capacitance of your capacitor. It's gonna be a very small capacitance in the picofarad. Then you're gonna insert a dielectric between the plates and see the effect. And then move to another set of capacitors, connect them in series and in parallel. Trust me, the connections are difficult and you're lucky because I'm gonna go do the connections for you and give you the results. This is something you will be missing. And eventually coaxial cable, which is only one trial to try, and we're gonna see the video together. Before I start practically, I'm gonna thank you for your emails and your messages. And I'm sorry if I was late replying to your emails, but just imagine how many emails I was having this weekend. So I was trying my best to keep up. So I still have few messages not answered. I'm sorry for that. I'm trying my best. So part 1 is this: capacitance versus the plate separation. Basically, this is what you have. It's a Pasco device. Pasco is the manufacturer. And you have 2 discs facing each other. And you can move the discs away and closer to each other. So D, small d, is your variable. The area of the plate, can you tell me briefly how to measure the area of the plates? Yes, anybody? So how do you measure, yeah?
Pi r squared.
Pi r squared. So what do you measure to be able to calculate the area?
The radius of the plate.
1 plate or 2 plates, or how?
I think per plate.
Okay, so, all right, Christopher. So basically, A is the common area. And since the 2 plates are facing each other on top of each other, like parallel and facing each other with nothing moved apart, you simply measure the area of 1 plate. How do you measure the radius, Maria? Any measuring tool you can think of?
Can we use a ruler to measure the diameter? We can put it like straight down, and then we divide it by 2, the measurement.
Okay, so you use a regular ruler, you measure the diameter, you divide by 2. Keep track of significant figures. The regular ruler, the smallest subdivision is 1 millimeter. You divide by 2. You measure the diameter. You don't know where the center is. If you want, you can measure the diameter 4 times and find the average. It's up to you. But think of these while you do the area. So the area is known or estimated with your measuring tool. Epsilon 0, do you know the value of epsilon 0? Yes? Maybe we can insert it here. So epsilon 0 is equal to 8.85 times 10 to the negative 12 SI units, right? Yeah, isn't it? So this is epsilon 0. Yes. All right, so let's keep it aside and let's call this the theoretical value of epsilon 0. Because when you finish the experiment, your job was to deduce epsilon 0. And maybe you will get very close to it or away, okay? So you will measure C with a certain device called the SCR meter. You measure D with a ruler. D is the separation between the plates. You will do 5 millimeters, then 10, then 15, then 20, or 0.5 centimeters, then 1, then 1.5, and so on. And you will measure C for each, okay? Also, you will have to connect those plates to your device. Maybe I can draw it for you, but I will definitely show you. So you see this nail, you connect it, and you have another nail in here, you connect it to your device. The device looks like a multimeter, and those wires that you can see here, they have a certain capacitance. So you have to disconnect your wires, put them on the desk, and measure the capacitance of your wires. You will get something like 1.3 picofarad, which is very small, but you have to minus this answer from all your measurements. Okay, do I make sense? You will also be asked to plot C versus D. Now my question is for Joanna. Is Joanna with us? Yes? Or maybe Nagam? Or maybe Rawan?
Yes.
Yes, I'm trying to guess who's speaking up. Rawan. So Rawan, if you plot C versus D, do you get a straight line?
Yes.
Do you see that C and D are proportional?
Inversely proportional.
Okay, so what do you think you should plot for you to be able to get a straight line?
C and A.
So if I plot C versus A is a constant, so I cannot plot versus A. So D is
1 over D.
Yes, so you will plot it as 1 over D. Okay, so you supposedly should get a linear relationship with a lot of fluctuation. Can you tell me what the slope represents?
Epsilon.
Yes, so C is your y-axis, 1 over D is your x-axis. So what does the slope represent? Epsilon?
Epsilon 8.
Exactly, so this would be your slope. So you would do linear regression, find the error on the slope, and then deduce epsilon 0, knowing that A is known and the error of it is known.
Yes, yes.
So you see, part 1 is basically time consuming. You have to do all these measurements, do the plot, linear regression, the slope, error on the slope, deduce epsilon 0, error on epsilon 0, knowing that A, you will have A with the error on it, maybe not, maybe I will give you the diameter, not the area, so I can give you some work to do because basically I'm doing part of the lab report. So part 1 is time consuming, I'm telling you from now, and we will do a practice at the end of this session. Thank you so much, Rawan. Now part 2. In part 2 is super quick. You do the measurements without the dielectric, or you insert the dielectric, you close on it, you take the measurement of C, let me call this CD a C dielectric. So you measure this one, you remove the dielectric without changing D, and you measure C again. So D is a constant. I'm gonna ask Michael, how do you find K, the dielectric constant, knowing C and knowing CD? Is Michael with us? If not, Lisa can answer. Lisa? You have a beautiful name, Lisa.
Yeah.
Yes.
If you want to find K, we can do CD over C.
Yes, you can simply do CD over C, knowing that the area is the same because we're dealing with the same capacitor. D is the same because while I remove the dielectric, I don't move the plates. By the way, this is experimentally difficult to do because when you remove the dielectric, the plates sometimes close on each other, especially if they're very tight. So while you close on the dielectric, you have to make sure not to close too much, like simply hold them. Hold the dielectric. When you remove it, D is considered to be constant. So D constant, A constant, they cancel out. If you do the ratio CD over C, you get K. My question for Lisa as well. My measuring tool, I mean this, the LCR meter is a digital measuring tool. How do you find the error on CD and how do you find the error on C?
Dr. Jessie?
Yes, Michelle.
Hello, Doctor. Doctor, are you recording the session?
Yes, I am. You have internet connection issues, right?
Yes, I had to re-download WebEx. It wasn't opening with me. I don't know why.
Yeah, it's okay. I'm going to record all the sessions every time you have a live session.
Okay, thank you, Doctor.
All right, back to you, Lisa. Lisa, you use the LCR meter, which is a digital measuring tool. How do you guess the error or the uncertainty on one measurement of C? Let's say it gives you, let me write a value of what I remember from my measurements. Okay, I'm sorry for this. What just happened? Okay, I need to insert a text box. Okay, so I remember I got something like 205.3 picofarads. Let's say I read this on my screen, you know, on the screen of my digital LCR meter. What do you believe the error is? So again, for a digital measuring tool, the uncertainty is the smallest subdivision. What is the smallest subdivision here? Anyone can help Lisa? Maybe Christopher or Joe?
2.1.
Ryan? Yes. What is the error?
0.1.
0.1 picofarad. Can you explain why?
Yes, because in a digital measuring tool, we just look at, so it's 205.8, so we just do one decimal. If it's more, then we just add the zeros.
All right, so let me repeat what Ryan was saying. Ryan said the measurement on the screen of the digital measuring tool, usually I take all the measurements. And I can see 4 significant figures, and I can see 1 decimal. So the error is 1 decimal, and the smallest is 0.1, because that's the smallest digit you can find between 1 and 9. All right, this is what I remember the values I got. But anyway, we're getting back to this one. So knowing CD, knowing C, you find K. Knowing the error on CD, knowing the error on C, how do you find the error on K? Who would want to help me with this one? So I need the error on K.
Error?
Yeah, error on K. Propagation of error. Yes, how do you do it?
So I do derivative of K with respect to CD and the error on CD.
So derivative of K with respect to one of the C's. So I'm going to start with CD. Knowing the error on CD, excuse my ugly handwriting, plus another parenthesis that would give me the derivative of K with respect to the first C. On your lab report, it's called C0. 0 means no dielectric. In this slide, it's called simply C, alpha C0. I know the error on C0. I know the error on CD. Now, if I'm going to find the derivative of K with respect to CD, how do I proceed? Anybody knows how to find the derivative of this function if CD is my variable?
So,
yes, Ryan or Michelle.
I have a question, but if we say derivative of A with respect to CD, so we consider CD to be the constant X, no?
You mean the variable X, yes. So it's like
yes, sorry, the variable. Okay.
Yeah, so it's as if you have X over C. What's the derivative? So if this is written as X over C, what will be the derivative? Anyone knows?
Minus 1 over C squared.
C is a constant. Michelle has an answer. Say it again.
1 over C.
It's 1 over C, very simple. So if your function is X over C, the derivative is 1 over C. Michelle, can you continue? If you have now C over X, what would be the derivative? The derivative of C over X. Yes, Michelle?
Wouldn't it be C?
It's gonna be minus C over X squared.
Minus C over X.
X squared. Okay, it's gonna be like this. All right, so I believe I helped you with this one. When you have a function to be A over B, you do the derivative with respect to A, then the derivative with respect to B. This is how it's gonna be for the first one. If you're not happy with the names, just use X and the 4. Maybe C is misleading for you. X over 4, the answer is 1 over 4 for the derivative. And if you have 4 over X, it's going to be minus 4 over X squared. So X in the denominator would give you a derivative of X 1 over X squared with a negative sign that is not important since you have to square both parentheses and then do the square root. Don't forget that the error has to be 1 sig fig, okay? So this is 1 sig fig, okay? I hope my slide is clear, and I'll definitely send you the edited version. So as you can see, part 2 is very simple. You will be given C and CD for dielectric 1, C and CD for dielectric 2, and you do the calculations, and that will be it. No plot, no linear regression. Part 3, the experiment is difficult, so my job, the calculation is very easy. You will be given a lot of capacitors. You will be asked to measure the first one. By the way, you will have some names to deal with. Let me explain. Nominal value and measured value and measured value and calculated value. I need somebody to tell me the difference between these 3 because you would need them for this lab. I stopped recording on, okay, thank you for telling me. Are you sure that I stopped recording? It's still recording. Yeah, I stopped sharing. Oh my God. Okay, I stopped sharing. All right. Anyway, I'm glad you still have my voice on the recording, and I'm glad you. How did you know, Lisa?
It doesn't show that you are screen sharing at the top of the
Yeah, thank you for
screen.
informing me. I was too busy with my slides. I knew something went wrong. Thank you. All right, which is not a big deal because I believe you need the recording for most of the sections and not, I don't believe anybody can watch 50 minutes unless you're really absent and you need to know what's happening and you have the slides. So thank you for informing me. Back to you. I need someone to help me out with nominal value, measured value, and calculated value. Do you see any difference?
The measured value is the one we use a certain device to find out. The calculated is the theoretical one. The measured is the experimental one.
Okay.
Isn't this true?
Yeah, so the calculated is what you calculate. The measured is what the measuring tool measures. The nominal is basically written on it. So you will be given many capacitors, C1, C2, C3, and it's written on it, let's say 42 nanofarad, 0.1 nanofarad, it's written on it. So you will write the nominal values. You will take the LCR meter and you measure each separated. And then you can measure the combination. How do you calculate C equivalent for a series connection? Who remembers?
It is 1 over.
Okay, and you have a, Joe, you can see some reminder in this table. So let me insert a text box without stop sharing because this is what happened a few minutes ago. If I insert a text box as an example, the example is you are given C1 to be equal to 22 nanofarad, okay? And you are given C2 to be equal to 44 nanofarad. What would be C equivalent in series? So C equivalent, I'm gonna call it CEQ. And what would be in parallel? Take a moment to give me an answer.
It will be C1 with the C equivalence would be 1 over C1 plus 1 over C2 to the power minus 1.
Okay, and the answer would be?
Second.
Yeah, every time have your calculators with you, especially for the last slide. I'm gonna give you something to try for 10 minutes. So you need maybe Excel, not your calculator, or both. Yes, C equivalent. For the parallel connection, it's easy. It's C1 plus C2. So this one is gonna be 66 nanofarad. For the equivalent one, I have my calculator with me.
It will be 14.67 microfarad. Nanofarad.
Nanofarad. I got the same answer as well. For the rounding, I'm gonna simply say 15 nanofarad. All right, because I have two significant figures, so I'm gonna round to two significant figures. So in this section of the lab, it's gonna be super easy for you. No data analysis required. I will give you C1, C2, C3. I will measure C1, C2 combined together. You do the calculations and you compare. So if they will ever ask you to find the percentage difference, I need somebody to remind me what is percentage difference. So how do you do the calculation if they ask you to compare? So every time they ask you to compare, you need to do the percentage difference. How do you compare, let's say, yeah.
Isn't the absolute the difference between theoretical experimental over the theoretical times 100?
Okay, so it's the absolute value of the theory minus experimental. In your case here, it is calculated minus experimental divided by calculated, if you want. Okay, and you do the
experimentally nominal.
No, we're gonna take the experimental to be the measured value. So this one is gonna be the experimental, and this is the theoretical. The nominal, we're not gonna use it. It's only to make sure to remember which is C1, which is C2. In other words, it's written on it 22 nanofarads or 20 nanofarads. By the simple fact of looking at it, we would know it's C1. So usually the nominal values are not accurate at all. We just use them as a name for my device, you know? So just keep it somewhere in your table to keep track of it, but try not to use it unless you have no choice. Okay? I'm done with part 3. So part 3 needs you to do some calculations, but nothing really difficult on the experimental level. The experimental level will be dealt by myself. Now part 4, you will be given coaxial cable. This is a picture of a coaxial cable. I'm sure you've seen one, of different length and different thickness. So, and basically different material inside. What is a coaxial cable? It's two cables inside each other. So one outside, one inside. You see that you have a copper mesh outside and a copper wire inside. So instead of having two cables, you have one and two cables inside. This is a diagram showing the radius of the first one and the radius of the second one, and L is the length of the wire. So for you to be able to find the capacitance of these two wires, aren't they wires facing each other and you have an insulator in between? So it has a capacitance. Okay, I will show you in the video in a moment how to connect it to your LCR meter. To find the capacitance to calculate, you need to measure L, you need to measure B, or usually it's given to you. You measure A, or usually it's given to you. And you can, so C can be measured by your device. LCR meter, you can find K easily. K is a dielectric constant of your insulator. Okay? So this section, you will be given one cable, you measure, another cable you measure, then you connect them together and you find C total. And then you will be asked, are they connected in series or in parallel? By the way, when you look at those cables, this is cable 1 and this is cable 2, connected by an adapter, you would think they are in series or you would think they are in parallel. You cannot really tell until you measure C total. And then you check, is it C1 plus C2? or it's the sum of the inverse, or is it the inverse of the sum of the inverse? Then you can deduce if it's series or in parallel. By the way, you need to minus the capacitance of your adapter, and for you to be able to do so, you measure with the adapter and without the adapter, so you can tell how much the capacitance of your adapter. I'm gonna give you all the measurements and you do the work, okay? Let me now move to the videos. I think we're ready for the videos. So
Doctor?
Yes.
I have a small question, please. The adapter, we can remove it?
Yes, the adapter is something you click. Usually I put the adapter to be able to connect them together. So if you want, I can measure C1 alone. I can measure C1 plus adapter. I can measure C1 plus C2 plus adapter. So I can guess what the adapter is. Okay?
So its only purpose, the adapter, is just to connect them both together?
Yes, and I will have another adapter to use before I connect to my LCR. So this cable cannot go into the LCR. I need an adapter, and I will show you how to connect your LCR. I hope the video will be clear because my videos are not the greatest videos ever. I'm trying my best and I'm not liking them so far. I'm trying to move the camera closer for everything for you to be able to see. So I'm gonna move to the videos. I'm not gonna watch them all just to show you at least the procedure. You watch them later. So I'm gonna repeat part 1, 2, 3, and 4. The videos are here. They are already uploaded on YouTube. Let me show you. Today we have only one video of 15 minutes. So maybe it's gonna be easier, I don't know. So let me see. In this experiment, we will explain capacitance and dielectric constants. What equipment do you see on the desk? You have a capacitance box on which you can read what the condensateur. You can see many capacitors. Okay, so this is the capacitor box that I will use for part 3, and you see the nominal values written on it. A capacitance from Pascal of a variable distance between the plates, and you see each plate is made of a disc, so a circular plate. You have the LCR meter. The LCR meter measures LC and R, which is the inductance, the capacitance, and the resistance of a resistor. So it's very precise. You have a multimeter that... By the way, the multimeter will not be used, so I'm gonna say that it's not gonna be used, but it was on the desk and I was misled. Used to calculate, to measure the potential difference. Why do we need it though? I don't think we really need it for this experiment, so let's keep it aside. Those are two dielectric, the material of which is unknown. Both are plastic, one is thick, one is thin, so maybe you can compare both. You have some banana wires. So yes, we know it's plastic, but you have 1 million types of plastic, so we don't know what really is. 4 or 5 banana wires, I don't know how many. You have some plugs for the LCR meter that you can use. You have the Pnc cables of different thickness, maybe, yeah, and some adapters. Okay, as you may have noticed. Okay, I'm gonna move faster. Okay, to show you how I'm doing the measurement. If you are being able to see what's on the screen. It also, you don't need to pick a scale, it actually does it. Okay, I need to show you how to do the measurements. Okay. Both wires are connected to the plates of the capacitor. Okay, as such. If I turn on the LCR meter, you would see 8.8 or 8.6. You see some fluctuation is happening, and this is okay. Why is it fluctuating? The capacitance of my capacitor would only vary if I move the plates, or in other words, the distance between the plates is varied, or if the wires are actually moved, because as you can see, the two wires, the distance between them will actually change your measurement. So if your measurement, if the cables and the capacitors, the plates are not moving, everything is rigidly fixed, you should have a constant value whatsoever. So I can read 13.3 picofarad. Don't forget to minus from this value the initial measurement of the cables. All right, so your job is to have a distance between the plates equal to 0.5 centimeter. So make sure you measure the distance between the two plates from the inside with a regular ruler. 0.5 centimeter you take a measurement, then 1 centimeter apart you take a measurement, 1.5 centimeter apart you take a measurement, and so on and so forth. You will only notice that as the distance between the plates increases, the value of the capacitance of your capacitor decreases, and the change is not linear. You will discover later as you do the plot. So again, for every measurement you take,
the change is not linear because C versus D is not proportional.
Your minus
I want to show you how to measure the wires alone.
Of the wires, let me take the measurement again. This is the, okay, let me keep them apart. So 1.3 picofarad.
So 1.3 picofarad was the measurement of the wires alone. So you have to minus this from your measurement. Now let me show you the part of the dielectrics. You watch this later. Okay, so in this part, you get ready with your capacitor and you put a dielectric in between.
I need to make sure that this is connected.
Okay, I'm gonna make it fast. Okay.
Okay, I'm gonna put it on to make sure it's measuring a value of the picofarad. Now your job is to close the capacitor in such a way that you have no air between the plates. So you're not supposed to be compressing the dielectric, and you're not supposed to have the plates loose or spaced, and you will have extra air in between. So make sure when you remove the dielectric, the distance between the plates is made not to vary at all. So with the dielectric, you do.
So you see the difference with and without. You can see the difference on the screen, maybe not, but you see the distance between the plates is not a variable. Now let me move to part 3. Part 3, we have to connect. Check it out.
One of the capacitors, okay? You will notice that the nominal values are written on the box, and the unit is microfarad. Again, microfarad is 10 to the negative 6. Picofarad was 10 to the negative 12. So this is 1 million times bigger than the values we were having, or more, you know. I just wanted to be able to compare, which means I will expect my SCR meter to change its unit automatically to nano or microfarad. It gives me 470.6 nanofarad, or something that could be 0.47 microfarad. This is called the measured value, and what's written on this one is called the nominal value. Nominal is what's written on it.
Okay, now let me show you how to do a series connection.
As such, so I will have a wire going through the capacitor, then I need to connect these two together. Let me try to do so. Okay, so if you imagine to have a current flowing in the circuit, it will go out from this terminal into the first capacitor, to the second capacitor, back to the LCR meter, and obviously this shows a series connection. So what measurement I will have here, it will be the equivalent capacitance of both capacitors C1 and C2 in series, along with the capacitance of the wire that I suppose is negligible in this case, so you can just ignore it because it's...
So for part B, no need to minus this answer from your measurements because this answer is picofarad, and what you have here is micro or nanofarad, which means it will go into the 5th decimal, so it will not make any change. Do you understand? And then you will be asked to connect these in parallel. So I already connected them in parallel. Then I will connect.
They are in parallel. And now I can connect the LCR meter to one of them. The LCR meter will be measuring the total or the equivalent capacitance of my connection, of my combination. So what you read here is not C1, neither C2, but C equivalent. And you will
which is C1 plus C2 in this case, since you have the parallel connection.
You're doing, and so on and so forth. You will be asked to connect C1 to 3 in parallel and in series and create random combinations, do the measurements. Eventually, they will ask you to calculate as well C equivalent to be able to compare your calculated value to the...
All right, now let me show you the PNC cable. So this is a PNC cable. I don't know, I want to show Michelle, everyone, and Michelle especially, the adapter used.
And you can see that this is a coaxial cable. So you have a cable outside, a cable inside, exactly like the case of the banana wires where you had two separate cables. So this is a coaxial cable. If I may measure the capacitance of this cable, I need an adapter. So I'm going to take the LCR meter. I hope it's visible on the camera. I can use this adapter, connect it into here, and then connect the cable and make sure the cable is straight somehow, because you don't need to trigger some distance variation in both. So make sure your cable is elongated.
So you measure the length and you measure the capacitance of the adapter alone. I hope you can see it. And then you measure without the, with the dielectric, I mean adapter plus wire. And you do the difference for you to be able to, like, you remove the capacitance of the adapter. I don't know if you see what I mean.
On the desk, put your LCR meter on, wait a second for it to give you a certain value. You see, it's 96.6 picofarad. Picofarad is a very small value for the capacitance, and therefore I would think maybe that the capacitance of the adapter will be affecting my measurement. After I write down this value, which is the measured capacitance of my first cable, I will make sure to measure the capacitance of my adapter and minus this value from all my measurements.
All right, now let me show you the second adapter, which is a female-female connector. It's here.
For cable number 2, measure the length and the capacitance. Eventually, you will be asked to connect both cables together. So this is a female-female connector. You will connect the first cable to the second cable and connect both to the adapter, like one terminal to the adapter. Maybe do this experiment on the floor to elongate.
Yeah, it has to be done on the floor, because on the table, I couldn't take a measurement. It has to be long and straight to be able to get a certain answer. Okay, and that's it for the experiment. Okay, do you have any questions before I move on? All right, now I'm gonna ask you to try this. So I'm on the appendix part. This is a small, let me call it classwork. It's not an assignment, it's not a homework, like let's do it now. Let's take around 10 minutes to do the following. And I want you please to throw your answers on chat, on private. I think you can do that. Plot, you don't need to show me. Linear regression, find the slope. Just tell me what slope you can get. If you do this on Excel, I think you need 2 minutes to get the slope. The error on the slope needs around 7 minutes. And try to guess item 4, which is a bonus. Are you ready to do this? Yes? Let me find our chat so I can follow up on you. Okay, I'm gonna go silent for a moment to be able to give you some time to think. And maybe stop recording, because this would be some dead time for the people watching the video later, okay?